Hi, everybody. It's Dr. Ricardo here. Just want to make sure that this is recording. We're going to do the PowerPoint lectures. I'm going to go through them with you for Chapter 17. So there's going to be two parts. I'm going to do the first 20 slides in the first part, and then 21 through 41 in the second one. So here we go. Okay, so here's slide number 2. So the idea is we've been studying weak acids and the way weak acids react. So here's the acid, acetic acid, which we sometimes abbreviate just HA. So HA dissociates to give you H plus and the acetate ion. So this is the counter ion. Okay, we typically write this as acetic acid plus water to give you hydronium plus acetate, but the idea is the same. If you were to add to the solution of acetic acid some external sodium acetate, so sodium acetate solid, that sodium acetate would dissolve and completely dissociate. Notice this is a one-way arrow down here, okay? So it's going to completely dissociate to make Na plus and acetate. Well, that acetate then, that added acetate by Le Chatelier's principle is going to interact with this equilibrium on the top, and there's going to be too much acetate, right? So if there's too much acetate, what's going to happen? Let me just put my tool on for a second. So the extra acetate that comes from this reaction that goes all the way to the right is the same stuff that's involved in equilibrium. So there'll be too much acetate in the solution. So what does Le Chatelier's principle do? Le Chatelier's principle would shift back to the left. So upon adding sodium acetate, the pH of the solution would go down, right? The pH of the solution would go down because some of the H plus that was further along on this side would go back the opposite way. So we'd expect the pH to go down because the amount of hydrogen ion concentration would get reduced, okay? Another way of saying it is we have an acid here and its conjugate base. If I add more of the acid, the pH will go up. If I add more of the base, its pH will go down. So that's the acid, and here's its conjugate base. So we're adding more of the conjugate base of acetic acid, so the pH of the solution would go down. So additional acetate, this is acetate, shifts the equilibrium concentration, lowering the H plus, going down. Okay, all right, next slide. Okay, so what we just looked at is called the common ion effect. Whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte ionizes less than it would have if it was alone in the solution. Okay? So let's take a look at an example, okay? Because basically what we're setting up is what we're going to call buffer solutions. So here's an example. And I'm just going to put my drawing tool on. Hang on one second. Oh, there it goes. Okay, so what is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution? So let's draw our beaker. Okay, so here's our beaker. Okay, I'm going to add to it 0.3 moles of HA, right? What's HA? That's the acetic acid. Okay, some people would call it HAC, but it's our weak acid, HA. Okay, so this is in moles. Okay, and then I'm also going to add to it same amount of its conjugate base, sodium acetate. Now, I don't care about the sodium part of the sodium acetate. I care about the acetate. So that's 0.3 moles of A minus. Okay. Okay. They're in there. And I add it. So there they are. Right? That's the HA. You just change colors. The purple will be the A minus. So they're in solution. And what's the total volume of the solution? 1 liter. Okay, so what are our initial concentrations? Well, if I have 0.1 moles of A minus in 1 liter, that makes its initial concentration, so I'll put the little 0, of A minus, right? Initial with the little 0. I could sometimes do this with parentheses too, as 0.3 divided by 1 gives me 0.3 molar, right? Dividing by 1 doesn't change anything, okay? Whenever I do my ice tables, ice tables have to be in molarity. Molarity. Here's my initial, here's my change, here's my equilibrium. That's what ice stands for. Okay, what else do I have? Well, I purposefully started with an initial concentration of HA. Okay, and that HA was same, 0.3. Right, 0.3 moles in 1 liter gives me 0.3 molar. Okay, so again, they do the simplified version. I would have written this plus water on the left. Right, water's not in equilibrium anyway. To give you, instead of H plus, we usually write hydronium over here. That's the same idea. Okay. Remember, in aqueous solution, these things are tied. So, acetic acid plus water. The acetic acid loses 1 hydrogen to make hydronium and the conjugate base acetate. Well, what's my initial concentration? 0.3 comes from here, and 0.3 comes from here. Why is this 0? Because you didn't add any HCl or any other place, so you have none of this. Now, in reality, in water, the concentration is 10 to the minus 7th, right? Because the pH of pure water is 10 to the minus is 7, so the hydrogen ion concentration is 10 to the minus 7. But 10 to the minus 7, guys, is so close to 0, right? 10 to the minus 7 is basically 0, okay? Basically 0. Okay, so adding or subtracting 10 to the minus 7 to whatever this is, x is going to come out, this is going to be negligible next to x. Okay, so we're always going to just start here and ignore the fact that water has a teeny tiny concentration of hydronium in it. Okay, so after I set up my initial line, how do I do the change line? Well, look at the stoichiometry. Has to go from left to right out of the gate. Why? Because I have to fill in the 0. I have to get rid of that 0. So for every 1 molecule of HA that reacts, that amount goes down by X. How much hydronium do you get? The stoichiometry says you get plus X. Look, one of these gets used up, one of these guys gets created. And I also, at the same time, create one of these guys. So it's 1 to 1 to 1 stoichiometry. Minus for reactants, plus for products. Okay, once I have that, let me just simplify this, erase all this stuff. The third line is very easy. How do I get the equilibrium amount? All I have to do is do the summation of these 2 lines. Okay, put together this and this. 0.3 minus x gives you 0.3 minus x. 0 plus x gives you x. 0.3 plus x gives you 0.3 plus x. Okay, once you have the equilibrium line, remember, the equilibrium constant expression always holds when you're at equilibrium. The concentration of H plus acetate in the numerator, the products in the numerator, divided by acetic acid in the denominator. Okay, I would have simplified this by, this would be my hydronium, this would be HA, and this would be HA, and this would be A minus. So I have all 3 of these. So what's going here? Well, this one is going to be X, right? This one's going to be 0.3 plus X. And what's in the denominator? Right, this is on the denominator. 0.3 minus x. Right? All of that is equal to Ka. Okay, I know the value of Ka. Here's the Ka that's given to you. Okay, well, guess what? X is going to turn out to be very small, right? The value of K is 1.8 times 10 to the minus 5. This is 0.3, okay? So even if this wasn't buffered, 0.3 is an enormous number next to 10 to the minus 5. This is 10 to the minus 1, this is 10 to the minus 5. That's 4 orders of magnitude, right? 0.3 is 100,000 times bigger than X, right? So if I subtract X from 0.3, it's going to be insignificant next to 0.3, so we're just going to leave it out, okay? If I subtract X, I'm not going to put the 0, we're just going to leave it out, right? Because here it matters because it's the only term, but X next to 0.3, subtracting from 0.3, and X plus 0.3 is insignificant. So let me just erase this little 0, because that's confusing, okay? So I'm going to simplify these by just leaving that guy out. So I can just go ahead and cross it out or just erase it. And that's what you're going to see written neatly on the next page. Let me just get my eraser. All right, we're going to just leave this guy out. Whoop, I'm going to just change the color and write over it. All right, just going to ignore this and ignore this. So all I'm going to have is X times 0.3 divided by 0.3 equals Ka. So the 0.3s are going to cancel out, and X is going to be equal to Ka. So let's take a look. Okay, so what happens? These two things are in the numerator, these guys are in the denominator. They're going to cancel out, which results in X being 1.8 times 10 to the minus 5 molar. And last thing, what is X? We'll go back one slide. Among other things, X is the hydrogen ion concentration. So now that I know the hydrogen ion concentration, I could just take the pH, right? So I need to take the log, the log base 10 of 1.8 times 10 to the minus 5. That will give me a negative 4.74. The pH has a negative in the formula. So a negative and a negative, the negatives will cancel out, and I'll wind up with 4.74. So let me just write that part down for you super quickly before we move on to another example. Okay? Now this is a very special spot. Right? This is called kind of the half equivalence point. This is when the solution has its maximum buffering ability. Because look what happens. You're going to get the concentration of the conjugate base, HA, is exactly the same. This is HA, right? HA was in the denominator. And this is A minus. I'm going to erase the H in a second. So the concentration of the HA and the A minus are going to cancel each other out. Let's get rid of this. So 0.3 here is going to cancel with 0.3 here. So interesting, X is just the Ka. Okay, let me show you this part. When you go to take the log of this number, you're going to get negative 4.74, right? That's what the calculator will give you after you do this function. You take the log of it. But our formula for pH has a negative sign in front. So what's a negative and a negative? The pH is always going to be positive for these guys. Okay? You have to have an incredibly acidic solution for the pH to go below 0. Okay? It's not going to happen in our weak acid, weak base problems. So that's the pH. Good. All right. Next one. Oh, let's go back to here. Sorry. Common ion. Did this. Oh, okay to drop the X. We just talked about that, right? Because X is going to be very small. And in the end, look how small X is. X is 1.8 times 10 to the minus 5. So it was definitely okay to drop the X. Let me just put that up just for a second. Right? Let me show you. It's always nice at the end to go back and look at what X turned out to be and see if your assumption to drop the X was okay. Right, once we're done, here's what we get for X. So is it okay to drop 1.8 times 10 to the minus 5 from 0.3? And here as well, right? Adding it to 0.3 wouldn't make a difference, and subtracting it from 0.3 wouldn't make a difference. This would be 0.2999 something. This would be 0.3. It would be a whole bunch of O's before I even got there. So that's why it's okay to drop the X here and drop the X here. Those two numbers are so close to 0.3, right? We have the 5% rule. As long as X comes out to less than 5% of the number that you're dropping it from, this is way less than 5%, right? This is 0.005%, or something like that. It's tiny. So it's definitely okay to drop the X. Okay, so the common ion affects weak bases in the same way. So let's say I have a solution and it's minding its own business, and it's a solution of our favorite base, ammonia. Okay, so here's my, here's our beaker. I have water and I have some ammonia in there. And the ammonia reacts with water. It is a Lewis base. It's an electron pair donor. It attracts hydrogen to it, so water is the acid in this case, to make ammonium ion and the residual hydroxide ion. So this is our Kb. So Kb means that it's a weak base. So not only do we have, doesn't go all the way to the right, so I don't get 100% ammonium ions, I'm still going to have some leftover ammonia. In fact, that's going to be the majority. So my equilibrium is, I've got both of these in solution. Okay? All right, well, let's disturb the equilibrium. So here we are. Right, I'm going to disturb the equilibrium by adding some external salt. Okay, so the common ion some salt. There's a pile of it. Let's add ammonium chloride. It's a very soluble salt. It contains the conjugate acid of ammonia, ammonium. Okay? Well, when this hits the solution, it's not the chloride that does anything, it's the excess ammonium, right? So those NH4 pluses create a common ion. So all of a sudden, the solution is going to be swamped with extra ammonium ion. So what does Le Chatelier's principle do? It shifts it back to the left. So some of this hydroxide will be used up and go back to water and ammonia. So that would mean that the pH of the solution, right, is going to go down because there's going to be less ammonium in it, right? Whenever the hydrogen ions are greater, that's when the solution is going to go down. So the pH would go down because this guy, right, this guy is going down. So when this guy goes down, the pH of the solution goes down. This is going to drop, right? So POH would be less, POH would be bigger, so pH would be smaller. So addition of ammonium ion shifts the equilibrium and lowers the hydroxide ion concentration. Okay, well, basically, the last two solutions that we just made, ammonia and ammonium together in the same solution, and acetic acid and acetate in the same solution. Whenever you do that, it's called a buffer. Okay? So buffers are specially designed solutions so that they absorb extra acid or base that you add to them. Okay? So here's some examples. Solutions of a weak conjugate acid-base pair that resist drastic changes in pHs are called buffers. These solutions contain relatively high concentrations, 10 to the minus 3 molar or more of both the acid and the base. Their concentrations are put into the solution in approximately equal amounts. Okay, so you can buy them, right, from the chemical supplier. This one is pH 10 buffer. It's designed to stay at pH 10. Even if you add additional acid to it, it's going to resist its pH going down. Okay, or if you added some base to it, it's going to resist the pH going up from 10. It's going to be stabilized around 10. Whereas water is not buffered at all. Water is at pH 7, but the tiniest bit of acid or base added to water will send the pH meter shooting in one direction or another. This pH 7 buffer in the middle, this yellow one, okay, this guy is much better than water at resisting the change of pH. There are chemicals in there. One is the acid and its conjugate base are placed into the solution on purpose. Okay, when somebody adds additional base to it, it's the acid form, the weak acid that reacts with it to absorb it. If somebody adds additional base to it, it's the weak. If somebody adds additional base to it, it's the weak acid that reacts to absorb it. So it's designed to stay around pH 7. Here's one at pH 4, so you can buy these. And what's in there? Now, there's just a dye to make it look blue and yellow and red. That's not the important thing. What's important is that both the acid and the conjugate base pair at a certain concentration are put in and it stays right at pH 10. This one, the acid and the conjugate base pair are put in to stay right at 7. This one, the acid and conjugate base pair are put at the correct concentrations to make it stay at pH 4. They might be a totally different conjugate base pair in this one versus this one, or it might just be different concentrations. So we're going to predict how to make buffers and what their pH will be. Okay, so ways to make buffers. Mix a weak acid and the salts of its conjugate base, or a weak base and the salt of its conjugate acid. Okay, so you're purposefully putting in the acid and its conjugate base, or the base and its conjugate acid. Okay, so I'm going to just draw that for you for a second. The other way to make it is to take some strong acid and partially neutralize a weak base, or add some strong base to partially neutralize the weak acid. So in this case, you'd be starting out with all HA, and then you're adding base to it to get an equal concentration of HA and A minus. Or you'd have a base and you'd add acid to it to get an equal concentration of B and HB plus. Okay, so those are the two ways to make a buffer. I'm just going to mark this up a little bit, especially the top one. Okay, so I'm going to purposefully put into the solution some weak acid, HA, and its conjugate base, A minus. Now, who cares how the A minus can come in the form of the sodium, but put those two things into solution, right, in about equal amounts, and I'll get a buffer. Right, put them both in. So I'm going to have a lot of both. Or I could take a weak base, B, and its conjugate, right? What's its conjugate? HB plus, okay? So I'll give you two examples, or two favorite examples. This case, this would be acetic acid and acetate. This case, this would be ammonia and ammonium, okay? Who cares how the salt can get in there? This could come in the form of ammonium chloride, Okay, this could come in this form of potassium acetate. What we care about is that we always have this mixture. Put them in on purpose, okay, in pretty large concentrations. Sometimes as much as like 0.1 moles per liter of this and 0.1 moles per liter of this. So that's the first way to make it, okay? The second way to make it is don't just go get bottles of both of these and pour them in and add water, but take the acid, right? The weak, that's got to be a weak acid, can't be a strong acid. Take the weak acid, HA, and then add some strong base to it, like sodium hydroxide, to get this to neutralize, to make A- on the spot, right? If I add sodium hydroxide to a solution of HA, the sodium hydroxide is going to react, totally rip off all of those H pluses to make water and leave behind A-. So what I would be doing is, if I had a 1 molar solution of this, I'd add a half a mole of sodium hydroxide, so that half of it would remain in this form, and then the other half would get converted to this form. And that's how I get my buffer, when I get both of those things in there at the same time. Okay? How about this last way? Well, what would happen if I started with some ammonium, okay, in my solution, and then I purposefully added the strong acid, HCl, to it? Well, HCl reacts completely with ammonia, right, to protonate this to make the conjugate base ammonium. Okay, so if I had a 1 molar solution of ammonia to start with and I wanted to make a buffer out of it, I would put a half a mole per liter of HCl. The HCl would neutralize the ammonia and create half a mole of this and half a mole of this. That, again, just 2 ways of making our buffer. Our buffer is a solution. It's like a designer solution where we purposefully have both the acid and its conjugate base, or the base and its conjugate acid. Okay, how a buffer works. Okay, so over here we have our initial buffered solution, right smack in the middle of the diagram. Okay, so I initially start out, I have my weak acid, HF. Hydrofluoric acid is not a strong acid, it's a weak acid. It only partially reacts with water to make fluoride ions and hydronium. So at equilibrium, I have both of these there. Okay, so this is my buffer. There's a large concentration of both. Okay, let's make it 1 molar, right? I'm going to have 1 molar of this and 1 molar of this. Okay, how did I get them in there together? Well, I added the HF directly, and then I added the fluoride ions by adding sodium fluoride. Okay, so now I have a lot of both. Okay, all right, what happens if I add acid to my solution? Well, if I add acid, which of these 2 partners is going to take on the acid? Well, this is an acid, so it can't react with an acid. It's F-. So if you think about superheroes, I have a superhero team, okay, of Batman and Robin. So Robin's going to say, hey, HF, Batman, don't worry about it. I'm the base. I will take on H+. And what does F- do with H+? Well, H+ comes in. F- is a weak base. So if in the presence of the strong acid H+, this is a neutralization reaction. This reaction will go all the way to the right, and all I will make is some extra Batmans back, some extra HFs back. So what did I do? I took the strong acid H+ and converted it to weak acid HF. So that's why the buffer solution is able to absorb hydrogen ions. It absorbs hydrogen ions because it converts the hydrogen ions from HCl, which was strong, to HF, which is weak. So at the end of adding the extra acid, the HF now is in a larger concentration, but at the F-. But look, they're still both in appreciable amounts. So there's a lot more buffering capacity to go, right? I didn't exhaust all of the F minus. I didn't use it all up. So this can live another day and absorb some more strong acids. Okay, so this is the way a buffer solution works. It can take on either an acid like we just showed, or it can take on a base like I'm going to show you in a second. So let me erase this screen. Okay, and let's go the other way. Okay, I have my HF and F minus in the solution. It's buffered. I'm starting off right over here. Use a different color. Right? Both of them exist. It's beautiful, buffered. They're both 1 molar. Now, all of a sudden, I add a super strong base, sodium hydroxide. Well, it's not the sodium that makes it basic. It's the hydroxide. So what is this? I just dumped all this hydroxide into the solution. So Batman and Robin are waiting. Well, this time, it's not the F minus, the conjugate base that's going to do the work. It's got to be Batman himself. It's got to be the acid, because an acid, the weak acid HF, will react with OH minus. So let me show you that. It's just a neutralization reaction. HF takes on the added super strong, dangerous base hydroxide. Nobody cares about the sodium, right? And this is a neutralization. Neutralization reactions, I make water, which is harmless. And if this H gets donated over here, what's left? F minus. So all I did was convert some of the HF. Look, they were both in equal molar amounts, the HF and the F minus. Now I've got more F minus than I do HF, right? Because I just made some extra, but I absorbed all that extra hydroxide ion concentration. If you did this to water, wow, oh my God, that pH would go shooting up if this was water, right? In our case, though, the pH is going to go up just a little. Ready to absorb the extra H plus. So it's like a pair of superheroes, one for the acid and one for the base, right? HF takes on the base, F minus takes on the acid. So that's how buffers work. Okay, how do you calculate the pH of a buffer? Well, we're going to use something called Henderson-Hasselbalch equation, which is really very simple. Okay, I'm not going to spend a lot of time on the derivation, but the idea is that in all of our buffer solutions, if we did an ice table, okay, X would be very small next to HA and A minus. So right away we know we're going to be able to drop the X's. Well, if we drop the X's, that means that in our Ka expression, which is right up here for any weak acid system, okay, we have the equilibrium concentration of H plus, the amount of A minus, which is the conjugate base, and the amount of HA. So basically, the initial concentrations of A minus and HA that originally put in the buffer are not going to change very much. And you can calculate the H plus based on knowing what the A minus that you originally had and what the H plus that you originally had and what the Ka is. So let me just write something down for that right away, and then I'll derive the equation. You don't need the Henderson-Hasselbalch equation. You could do this simply like this, right? We know this. We know this because we're saying X is small, so the initial concentration of A minus is not going to change very much. You can just put it in. You can use the initial concentration for the equilibrium concentration. Same thing with HA, because if we did our ice, this guy would be X, this guy would be A minus, the original concentration plus X, and this would be the original concentration minus X. But if X is small, we can just go ahead and use those numbers. Well, if I have three things, I can just do what? I can just solve it for the last one. So I could just do this. H plus, now for a buffer solution, because they don't vary very much from their original amounts, the H plus concentration would be equal to Ka is in the numerator times what? This one is in the denominator times the original concentration of the acid, Ha, all divided by the initial concentration of the base. So this guy would go underneath, right? So that's all you have to do. Nothing fancy. And then once you have H plus, you can always get pH from H plus. Okay? Well, the Henderson-Hasselbalch equation takes the logs of this equation, right? So if I take minus the log of the left-hand side and minus the log of the right-hand side and follow the rules for logs, I get this equation here. Here's the definition of pH, right? Look at that, right? Minus the log of H plus is the same thing as pH. Minus the log of Ka we call pKa. Okay? And the log of a number divided by the log of the other number, okay? This one I just rearranged them and I put the concentration of the base here and the concentration of the acid here. So just this guy is negative plus a negative over here, and the way the rules for logs go, that if I take the positive version of it, these two things are going to flip. Look, this one has a minus in the numerator and HA in the denominator. This one has the opposite. Well, that comes from the rules of logs. So this is a very nice equation. Look at it. The Henderson-Hasselbalch tells you the pH of a buffer solution is equal to the pKa of the acid-base pair that we use to make the buffer plus the log of the A minus concentration over the HA concentration. Now, guys, you can put little zeros here. These are initial concentrations. This is what you put into the solution. Because in a buffer, remember, X is going to be very small. You're going to have so much H plus in there. So much HA and A minus around that when the equilibrium goes either left or right, the amount that they're going to shift is going to be very small. Okay, so X is small, and if X is small, we can drop the X's from these two pieces. So X is going to be small. Okay, in our ice equation, and that will make this, instead of being A minus plus X and HA minus X, they're just A minus, initial concentration of A minus and HA. Okay, so we're going to try one out in a second. So this is very useful. It works only for buffers because buffers we're sure that X is small and we can drop it and we get this very nice situation. Okay, so let's try one out. What is the pH of a buffer that is 0.12 molar in lactic acid? They call it HL. H for the ionizable proton and L for the rest of the molecule. So this whole thing is going to be HL. And 0.1 molar in sodium lactate. Okay, what's sodium lactate? This whole molecule minus an H and a sodium in its place. Okay, so the Ka for lactic acid is 1.4 times 10 to the minus fourth. Okay, so what are we going to do? We're going to use the Henderson-Hasselbalch equation for this, but first let me just write the equilibrium out. Oh, sorry. Just trying to open my writing tool. Ah. We'll get it. Oh. Okay, so this guy, we're going to abbreviate HL. The L is for lactic, for lactate. So there is the HL, and this guy, the sodium lactate, is going to be L minus. So what's our equilibrium? Lactic acid, HL, plus water, it's a weak acid. We know that because look at its Ka, how small it is. Okay, weak acid to make hydronium. And L minus. Okay. All right. If we did the whole ice table, we would get this guy would be X. This guy would be L. We X this. Plus, but it's going to be small next to this guy, right? This is the one that's going to add on because it's got to come out of the gate by going to the right to make a little bit of X. This is going to be the initial amount of HL plus X, right? This is the initial amount of HL minus X, and we leave water out. So we would get Ka is equal to this times this divided by this. Okay, but remember X is small, so okay to drop the X. X is small here, drop the X. And Henderson-Hasselbalch will work. Okay, so here we go. The pH is equal to the pKa plus the log of the lactate divided by the lactic acid. So the definition of pKa, okay, sometimes you have the pKa, this time we only have the Ka, is just take negative log base 10 of the Ka. So they gave us the Ka, we're going to take the log of it, and then drop the negative sign. Okay, so when I take the log base 10 of 1.4 times 10 to the minus 4th, that's going to give me a negative 3.85. Okay, and then put the minus sign on the negative 3.85, and I'll get 3.85. So that's just, this is just doing this over here. Okay, and then over here, I have to have plus 0.08. How do you get this 0.08? This 0.08 is this work right here, which is the log of 0.1 divided by 0.12. So you just need to do this, right? And it's positive, right? You don't have a negative sign on here. So this is the concentration of the weak base divided by the acid. So we put this guy in the numerator and this guy in the denominator. So I need 0.1. Well, that's so close to 1, right? Basically, they hardly change. This guy's 0.1. It's almost a perfect buffer. So I just need 0.1 over 0.12. And then take the log of that. Okay, so let me do 0.1 over 0.12 for you. Going to be a number like very close to 1, just a little bit south of 1. 0.1 divided by 0.12. Okay, I get 0.83, and then if I take the log of 0.83, log of 0.833, and I get negative 0.078, and that's what they got this here. Okay, so I get 3.85 minus 0.08 gives me 3.77. So that's the final pH of the solution. So let's erase all this. What does make sense mean? Well, makes sense to me is if I have a little bit more of the acid than the base, it should be lower than the pKa, right? And if I have a little bit higher than the acid than the base, it should be a little bit bigger than the pKa. So which one is predominant? They're not tied, right? They're not both 0.1. I have a little bit more acid. So that's why I have to subtract from my pKa. If these two guys were tied, what's the log of 0.1 over 0.1? Well, 0.1 over 0.1 equals 1, and the log of 1 is 0. And that's when pH is equal to the pKa, when the concentration of A minus is equal to the concentration of HA. This whole term will drop to 0. Okay, right? Good. Okay, so in our case, we're going to be a little bit lower because we have a little bit more acid than we have base. Good. Okay, the next slide is called buffering capacity. The buffering capacity is the amount of acid or base the buffer before the pH begins to change to an appreciable degree. The more you shove into the solution, the higher the concentration, the higher the buffering capacity. It's like you're getting more soldiers, you're getting more Batmans and more Robins. Okay? Remember, Batman takes care of any incoming base that comes in, and Robin takes care of any incoming acid. So the higher the concentration, the bigger your army of acid-base conjugate pairs that can knock out any strong acid or base that you put in. The pH will be the same for the conjugate base pair of a 1 mole, if it's 1 molar or 0.1 molar. Isn't that interesting, right? So the pH will be exactly the same if you put 1 molar acetic acid and 1 molar sodium acetate as it will be if you put 0.1 molar acetic acid and 0.1 molar sodium acetate. The difference is the 1 molar solution has a lot more soldiers, so it'll have a much higher buffering capacity. You can neutralize more acid or base before the pH changes appreciably. Kind of makes sense, right? You've got that many more HAs and A minuses available to neutralize strong acids or strong bases that come in. Okay, how do you do the calculation? Well, this is a kind of a nice slide, and it goes through the two-step process to figure out what is the pH of a solution that's made from when you add a strong acid or a strong base to a buffer. So let's go through it step by step. So in the red line up here, we're going to follow all this and go all the way to here. Then we're going to do the same thing for the blue. Okay. Right? So we have a buffer solution. So it's a solution that contains both acid HA and its conjugate base A minus. We add acid or hydrochloric acid. Okay, so let me just write that down. Just hang on one sec. Okay, so I have my buffer, everybody's perfectly happy, and what do? I perturb it by adding some strong acid HCl. Okay, if I add some HCl, the first reaction I have is the neutralization reaction. The neutralization reaction goes all the way to the right. Any reaction that produces water as a product, water is a very stable substance, it's going to go all the way to the right. Okay, so if I add HCl, who's going to take on the HCl? It's got to be the A minus. This is an acid, the strong acid HCl. Its active ingredient is really just H plus or hydronium. And A minus, it's the Robins who will take it on. So A minus reacts with H plus, goes all the way back, makes a little bit more of HA. Okay, so the first thing I do is I have to stoichiometrically determine how much H plus did I add. which of these two things was in the limiting reagent. Okay, so I have to do this part in moles. How do I get moles of something? I take its concentration times its volume. So do this part in moles. So I get the moles of A minus that reacted plus the moles of HA. I figure out which of the two is the limiting reagent. Usually, if I don't exceed the buffering capacity, I'm going to run out of H first. So this will be the limiting reagent. Okay? That means there'll still be some A minus around after. It's going to be less than before, and there'll be some HA. I take the results of the neutralization reaction, and now I know the new amount of A minus and HA that I have in solution, and I can use the Henderson-Hasselbalch equation or just my regular KA equation and do an ice table for part 2. And the ice table will allow me to calculate X. X is going to be, among other things, equal to hydronium, right? So if it's equal to H plus, then once I get X, after the ice table, I can easily get pH. Okay, so go through that one more time. Let me erase this. Okay, and I'll just say it verbally. Two-step process. The first reaction is a neutralization reaction that you take care of in moles. Once you figure out what's left over after that neutralization reaction, you take those initial products and plug them into either the Henderson-Hasselbalch equation or the Ka expression to calculate H+. Then once you get H+, you get pH. Okay, so 2 steps. Neutralization followed by equilibrium. Okay, neutralization goes all the way to the right. Okay, it's not 2 equilibriums, it's a neutralization and an equilibrium. Okay, well, what's the other side of the coin? The other side of the coin is I have my buffer solution, and this time I'm going to add some sodium hydroxide to it. Right? Sodium hydroxide is the strong base. So who takes on sodium hydroxide? It's the Batmans, it's the HAs. Right? The active ingredient in sodium hydroxide is OH minus. So I need to calculate the moles of OH minus by taking its molarity of the original solution that I added times the volume of that solution. Molarity times liter gives me moles. If I know how many moles of sodium hydroxide, moles of HA that I started with. Okay? If I don't exceed the buffering capacity, meaning I don't use up every bit of HA, that means this will be the limiting reactant. I'll run out of this. Now, at the end of that process, I'm going to have a certain number of moles of this, certain number of moles of this. Okay? I figure out what the volume of the solution is, get those guys back to volume, back to molarity, and now I have a buffered solution with some HA in it and some A minus. Well, we know how to calculate the pH of that. We can use the Henderson-Hasselbalch equation or just our Ka expression. Calculate the H plus or the hydronium. Once you get that, the next step, it's very easy to get the pH. pH of anything, if you know the hydrogen ion concentration, is just minus the log of the hydrogen ion concentration. So just like up here, it's neutralization followed by equilibrium. And in the equilibrium, only the second one do you need to do an ice table, okay? Or you might not even be able to skip an ice table if you use the Henderson-Hasselbalch equation. Okay, let's take a look at it. About 0.3 moles of acetic acid and 0.3 moles acetate to enough water to make 1 liter solution. Calculate 0.2 moles of sodium hydroxide is added. Okay, so let's draw the original solution and let's talk about what we're adding to it. Okay, so neutralization followed by equilibrium. Okay, even though this looks like an ice table over here, this guy is not going to be an ice table. This is going to be a neutralization table that you could have done in Chem 1. Neutralization, we just do it stoichiometrically. So our neutralization table, you're allowed to do in moles. Don't ever try to do an ice table in moles. This is not, even though it has before, change, and after, notice it doesn't say equilibrium. This is not an ice table. We don't have any X's. That's part 2. We don't have an equilibrium here. That's okay. Neutralization reaction. Okay, all right, so let's draw the beaker. Here's my beaker. I have 0.3 of this. What is this? This is our HA. And I have 0.3 of this. This is our A minus. Okay. The solution has a volume of 1 liter. So originally, right, before any chemistry happens, what's the initial concentration of HA with the little 0? 0.3 divided by 1 gives you 0.3. So this guy's 0.3 molar. Okay, what's my initial concentration of the conjugate base? Acetate. Initial concentration of acetate. Again, 0.3 in 1 liter. 0.3 divided by 1 gives you 0.3. Okay, so they're both in the solution. Here's the HAs. A lot of them. And there's an equal amount of the other guy. Make those black. They're sitting in there waiting for somebody to dump acid or base in. So these are going to be these guys. These are going to be those guys. Okay? All right, now what do I do? Someone comes along and they take 0.2. Now they gave it to you already in moles. If they gave you the concentration and the volume, you'd have to calculate moles. Remember, moles. We don't care about the sodium. We care about hydroxide. So wow, I'm going to add 0.02 moles of OH minus. Okay. Well, which of those two is the OH minus going to react with? It's going to react with the HA, right? Because an acid will react with a base. Okay. So let me erase this stuff down here and just do the work down here. Okay. All right. At the start of the reaction, let's write out the neutralization reaction. Here's my neutralization reaction. Neutralization is not an equilibrium reaction. It goes all the way to the right to produce water. Neutralization is HA, the weak acid, acetic acid, plus hydroxide. Hydroxide is a crazy strong base. It's going to pull that HA directly off. Water is not even going to be on the reactant side. It's going to be one of the products. If hydroxide steals an H+, it makes water. Okay, and what else does it make? A minus. So I exchange the strong base sodium hydroxide for the weak base. Right? That's how many moles per liter they are, but it was a 1 liter solution, so it's also the same number of moles. And they told me I added 0.02 moles of this. Okay, so go back to Chem 1. Got a 1-to-1 chemical reaction. This is 0.3, this is 0.02. This guy right here is the limiting reactant, right? I'm going to use every bit of that 0.02 up because it's so much less than this, right? For each one of these that's going to react, it's going to react with one of these to make one of these and one of these. So let's do the stoichiometry. Okay, how much does it change? Okay, well, we're allowed to make a change column even though we're not in an ice table. So we're going to say, if it's the limiting reagent, it means I'm going to use every single bit of that sodium hydroxide up. LR means limiting reactant, and there's going to be nothing left. There's always nothing left of the limiting reactant. Remember that from Chem 1? You always use up all that stuff. The limiting reactant will always go down to 0. Okay, look at this. HA is on the left. So for every 0.02 that gets used up over here, 0.02 gets used up over here because it's a 1-to-1 stoichiometry. One of these reacts with one of those. Sorry, that's a 1, not a 2. Okay. So I use that up. Well, these guys I have numbers for. 0.3 minus 0.02 gives me 0.28. Okay. How much sodium acetate did I have to start with? The amount of acetate was 0.3. Look where it is on the right-hand side. For every hydroxide that gets used up, I create 1A minus. Right? That's why it goes. So I had 0.3 to start with. It goes up by 0.02. At the end, 320. Okay? All right. Now, these guys are in moles. I can take these numbers, if I put them back into concentration in molarity, I can put them into the Henderson-Hasselbalch equation. So I'll do that on this page for you, okay? The Henderson-Hasselbalch equation is a way to calculate the pH of a buffer solution. You see, guys, the product after the neutralization is a buffer solution. Look, a buffer solution is a solution that has an appreciable amount of the acid and its conjugate base together in the solution, right? So they don't tell me the volume of this sodium hydroxide, so it must have been negligible. So that means if this was a 1 liter solution and I have this many moles, if I divide it by 1 liter, I'm going to get the same exact number for the molarity. So this is the molarity of the weak acid HA. Okay. Divide this by 1 liter. See, if they would have told you I had to add 5 milliliters of solution to get that 0.1, then I'd make this not 1 liter, but I'd put that extra little volume in to be sure, and this would be 1.005 liters, right? Because of that extra little bit that I put in. So that's extra 5 milliliters that I put in. But they didn't tell me that. They made it easier for me. They just told me it's kind of like I put solid sodium hydroxide in, so I didn't even have to worry about it. Okay? But in the harder questions, you're going to have to account for the total volume of the solution. So take the moles from the neutralization reaction and divide by the total volume of the solution. Here, our total volume didn't change. Okay, now, the nice thing about the Henderson-Hasselbalch equation is if you have the equilibrium concentration of the acid and the base, you can calculate pH, right? pH is equal to the pKa of the acid. So you can look up the pKa of the of acid, HA, divided by the base. So these are opposite, okay, because we changed this sign to plus. Okay, so this guy, this is the acid, it's going to go here. Oh, I shouldn't use B, I should use A. That's confusing. This guy goes here. And the pKa of the acid goes here. If you don't have the pKa, just put in minus the log of the Ka. Okay? If you have the pKa, just put the number in. Okay, let's see how it turns out on the next page. See if I got that right. Okay, so the pKa is given to you at 4.74. And then the log of the 0.320 over 0.280 gives you 4.80. Now, let's see. In this case, what did we add? We added some sodium hydroxide, so the pH went up a little bit. Back one slide and see if I got that right. I said the formula was the, right? I said it was the acid. Let's go back to the Henderson-Hasselbalch and see what sorry, with this guy, the plus, it's the base over the acid. Okay? So I had that wrong. Just go back to here. Okay? So just have the formula in front of you. I don't usually use this. I actually just go back and calculate it from the Ka. So we want the concentration of the base divided by the acid. So come back over here. I'll just redo it. Oops, sorry. Okay, when we got to here, we want the base, this guy in the numerator, and this guy in the denominator. Okay? So I'll just do that again. For you, we want the base over the acid. Sorry about that. And we said these guys were basically equivalent to the concentration because we had exactly 1 liter solution. So again, pKa, pH is equal to pKa. If you look up the pKa of acetic acid plus the log of the base over the acid. Our base is A minus. Our acid is H plus. Excuse me, HA. This is all in parentheses. This one goes in the numerator, right? That's A minus. That's HA. This one goes in the denominator. Why is it okay to put moles in here? Because I had a 1 liter solution. So these are not only moles, they're also molarity, because remember they were divided by a 1 liter solution. So they're concentrations as well. Divide by 1 liter, you still get 1 molar. So that's nice about the Henderson-Hasselbalch equation. You'll see the next one. So we have the plane. And the 0.28 in the okay, almost done. We're just going to finish with the last 4 slides. What is the effect of a base on a buffer versus water? Okay, so we're going to do a comparison here. The left-hand side is A, and we're going to compare it with B. So the breakdown is right here. So I just get my drawing tool. Just hang on one second. Sorry about that. Let's compare this side with this side. Okay, so I have a 1 liter solution of buffer. It's pretty strong. It has a strong buffering capacity. It's 0.1 molar in acetic acid, 0.3 molar in acetic acid, and it's 0.3 molar in sodium acetate. So it's ready for the addition of sodium hydroxide. Who's going to take on this 4 molar sodium hydroxide? It's a very concentrated solution of base. It's only a little amount. Who's going to take it on? Is it going to be the acid or the base? Well, if I'm adding a strong base, right, it's got to be Batman. It's got to be acid. Who's going to do it? So I'm adding the strong base sodium hydroxide. This guy's going to take over. This is going to just sit on the sideline. In fact, it's the product's reaction. Okay, well, look what happens. If I add 5 milliliters of this incredibly strong solution of sodium hydroxide, the pH only goes up 0.06 units. It goes up from 4.74 to only 4.84. It still goes up, but that's an incredible job of buffering, right? So if you had this in your stomach and you drank this sodium hydroxide, your stomach could handle it. Your stomach could buffer it, okay? Ready to go, right? Well, what happens if I took 1 liter of solution that's totally unbuffered? It's got nobody to fight. It added that same stuff. 5 milliliters of 4 molar 5.3 pH unit. So if you subtract 12.3, take 7 away, how much did it go up? It went up 5.3 pH units. Now remember, every pH unit is 10 times more basic than the one before it. So 5 means 100,000 times more basic. This thing has 100,000 times more hydroxide ions in it than this guy over here, than it did before, right? 100,000 times more hydroxide than it had before. Because, right, 1 pH unit, pH is a logarithmic factor, right? 1 pH unit means 10 times more acid. That's if the pH is going down. The pH is going up, it's 10 times more base. So this is 100,000 times base because it's 5 pH units, right? Every pH unit that you go up is 10 times more basic than the one before it. Okay, so we're going to do the calculation here in a second. But last thing I want to show you from this slide is, this is not a mystery, okay? How many moles of this we're going to need? So how do you get the number of moles? Moles of an added material, just like in Chem 1, moles is equal to the molarity of the solution that you're adding times its volume in liters. If I want to know the moles of this that's added, I take the molarity of this, that's just 4, that's easy. Don't touch it. 4 molar. Remember, what's molar? Moles per liter, right? So that's hard to write, but I'm going to write moles per liter. That's what capital M means. Okay, what's 5 milliliters in liters? Okay, well that's going to be 1. If I put the 5 here, that would be 500, so that's not it. If I put the 5 here, that would be 50. That's not it. That's the 5. That's 5 milliliters written in liters. So 4 times 0.005 liters, the liters cancel out. And how many moles would I be adding? Not a huge number, but it's something. The moles would be 4 times 5 is 20. So it would be 20 times 10 to the minus 3. 1, 2, 3. Or 2 times 10 to the minus 2. Okay? just to make sure. That's right, 20 times 10 to the minus 3. If you want to write in scientific notation, 2 times 10 to the minus 2. So that's a lot of moles. Okay, let me check. Point 0.05 equals 0.02, which is 2 times 10 to the minus 2. Okay, so just adding 2 times 10 to the minus 2 moles of the strong base sodium hydroxide, the buffer hardly moves, but water would go up to pH 12 from pH 7. Good. Okay, let's do the example. So here's what I just did. First step, calculate the number of moles of sodium hydroxide. So that's right here, 2 times 10 to the minus 3. Okay, take that. I took that, and the number of moles of sodium hydroxide divide by 1.005 liters. Why? Because I had 1 liter of solution, of buffer solution, and then I added the 5 milliliters. So the concentration of 0.00199. So guys, in this one over here, to do it for the water, okay? So there is, I react to it, so all I have to do is calculate what the concentration of sodium hydroxide is in the solution. Okay, so let me get my tool and then show you how to do it. So the top one, I think they got reversed, right? It seemed like all right, so this is for the water one. Okay, so this is adding 5 milliliters of 4 molar sodium hydroxide to water. What would the pH be? Okay. I guess what happened with the question that I have at the bottom of the page before is not exactly the same one as in that graphic. That was 2 pages before. So we'll do this one. Okay. All right. So everybody see that? This is just molarity times volume gives me moles. And then I want concentration, so this is 1.005 liters because I'm accounting for the 5 milliliters of the sodium hydroxide solution that was added to the 1 liter of water. Okay, so this is the concentration of sodium hydroxide. Once I have the concentration of sodium hydroxide at equilibrium, I can get the pOH. pOH is just minus the log base 10 of the OH minus concentration. So if I take a log of this, I'm going to get negative 2.7. So 14 minus 2.7 gives me 11.3. And now we're starting out with a pH of 7. So I wonder why this is different than the one before. Okay. In part B, the same number of moles of sodium hydroxide is added, okay, which gives us 0.289 moles of acetic acid. All right, because this guy, remember in the neutralization reaction, is going to get subtracted from 0.3. So I had 0.3 of this, and I have to subtract 2 times 10 to the minus 3 to give me this. And then divide it by my volume, which is 1.005, will give me the concentration of it. And the amount of acetate is going to go up, right, by 2 times 10 to the minus 3. Volume, and then you plug those two things into the Henderson-Hasselbalch equation. This is the concentration of the A minus, right? You take the conjugate base, always divided by the amounts of the acid, HA. Okay? I would have been a little bit more careful, and I would have just went one more step. Let me erase a little bit over here. Right? We want to be careful. I don't like this plugging in moles like they do. Okay? I would have taken the time. You would have got the same answer, but I would have taken the time to put concentrations in. Right? Because then has back concentration. What I and I would say, okay, I have that many moles of HA that are remaining. So what's my concentration? Take the moles, divide it by the liters, right? We should use the formula correctly. So what is the moles? The moles is 0.298 moles. And I added 5 milliliters to a 1 liter solution, so this volume goes up a little tiny bit. I don't think you should get sloppy. This is moles. Guys, this is moles too. Divided by that 5 milliliters made a little difference. Not just 1 anymore. So this answer should go in for the here. It's going to be so similar, right? Just the tiniest bit different. Okay, now, granted, in the numerator and the denominator, I have exactly the same thing here, so they would have canceled out. Okay, so you will get exactly the same answer, but be careful. When you do buffer solutions, you're going to add, when you do titrations, you're going to add an appreciable amount of new liquid. So the volume is going to change a lot. I don't think oh, the last thing, look how small this solution went up. This thing was so buffered. 0.74 to 4.75. It went up because I'm adding sodium hydroxide. Okay, I just want to go back and look at the question. Okay, so this guy is not exactly the same. Okay, let's see what the difference is. This was A over here. Okay, see what happened is the A's and the B's got switched, right? This is really B over here. This is B here. And this is A over here. Okay, I'll leave it alone, but you see how they got switched? But it is the same question from here. So I don't know why do we get 12.3 here? See if they did something different. Take a look. On the next page, they don't get 12.3. They get 11.3. Let's see which one is right. So let's assume that the 2.7 is right. Okay, so I have 14 minus 2 point, right here. Okay, this should be 11.3. Just double check it. All right, so this is times 10 to the minus 2. Then I have, let me take the POH of that. So let's do the log of 0.00199. So this is right here, not here. So this graphic that's in the textbook is incorrect. This should not be 12.3. This should be 11.3. Okay, it goes up 4.3 pH units, not 5.3 pH units. Okay, that's the end of it. Okay, that's actually a good place to stop. I will pick up the next video starting with titrations. Okay, thanks for your patience.